We've already taken a look at how do we go through find the equation with least squares line. We took a look at the correlation coefficient, and so far we've just assumed that all the data is linear, which is great, except for that most of the relationships that actually occur in real life are not necessarily linear. All right, so we have sinusoidal for temperature quite often. We have quadratic for businesses, that sort of stuff. Even radicals and stuff like that for relationships. They're probably seeing differential equations, etc. So what can we do to be able to possibly linearize the data? And you might be asking, well, why do you even want to do that? So we know sometimes bivariate data does not have a strong linear relationship, all right? Or if I have a strong nonlinear relationship. And it could be helpful, not saying it always is, but it could be helpful to transform it into linear because linear relationships are really easy to work with, especially if we have to do things by hand. So let's say we know what type of nonlinear relationship we're working with, and we actually know a decent model to be able to um, try to model that data that's nonlinear. Then what we can do is we can kind of use an inverse function on the explanatory variable. And then we can go through and just do some algebra and be able to isolate that explanatory variable after we've hit it with the inverse function. So for instance, okay, this is just one example. If we have data that fits the power form, okay, so y equals alpha x raised to the beta, where x is going to be the independent variable, or so what we can do is we can just go through and hit it with a natural log, and then use, remember this one from pre-calculus, where if you have two things being multiplied or two factors being multiplied, then the natural log, you can just split those off, right? So remember that stuff from pre-calculus, all that fun. And then one other rule you might remember from pre-calculus is that you could take the exponent and move it as a coefficient for logarithms. All right, so now I just used ln. We could use any base of log, but ln is just the easiest. All right, and to be able to solve for y, what we could do is we could just take an exponent of those sides. So in reality, we could just cut and paste this if we wanted to. All right, and we could say that y is going to be equal to the exp of all this stuff. All right, and that would linearize it. All right. Um, And that's what we're trying to get to, is we're just trying to linearize this data to be able to make it a little bit easier to work with. All right. So if we have like this perfect exponential relationship or this perfect power relationship, we can hit it with an inverse function. Okay. It's sort of like, for those of you guys that have taken differential equations, hitting it with a transform. All right. Um, and we could just go ahead and hit it with a transform or a linearization and just turn it into a linear sort of relationship. Same thing here with the power. Same thing with this sort of relationship that almost looks logarithmic, is we could just hit it with a linearization. So pretty cool that we could just use some basic algebra, and we could just go through, linearize it, and then make it into something simplistic. All right. Now, let's take a look at an example of how we might do this in MATLAB. All right. So on average, we have the surface area of humans is related to the weight. And let's say for some reason somebody went through and they took the weights and they also took the surface area of several human beings, and they came up with these numbers. All right, and they recorded them. And then somebody went through and they found a pretty good power model for this. All right. And again, it has to be a pretty good power model, because if it's not pretty good, then the linear relationship's not going to be good. All right. So we want to linearize the data, and we want to write some MATLAB code to do the following. All right. So we're going to find the function to linearize the data, which we're going to have to do by hand. And then we're going to create a scatter plot of the original data using the power model, and then a scatter plot of the linearized model. Let's use the subplot function, put them side by side, find the correlation coefficient of the linearized data, and then finally print the correlation coefficient and the equation of the linear model to the screen. All right, so first things first is we actually have to code the data into MATLAB. So I'm going to do that first. So let me just go through. I'm going to pull this off to the side so I have it to see. So I'm going to call W equal to the original data, which was 70, 75, 77, 80, 82, 84, and 87, and 90. And then we have the area, or the surface area in this case, of our human beings, A, And that's going to be equal to, we have 2.44, 2.51, 2.53, 2.56, 2.57, 2.58, 62, and 2.63. All right, so that's fun. Now, it says that we want to linearize the data. All right, so now I'm just going to plug this in here, that our relationship, and I'm going to create a Sims variable for this, for capital W and capital A. We have that capital W is going to be equal to 0.825 times, and it's going to be a vector. So I'm going to say dot A dot raised to the 0.258 power. All right, now that doesn't mean anything yet, but what we have to do is we have to linearize this. All right, so I'm just going to do the algebra as I'm working through this. All right, in Matlab. So what we could do is we could just take a natural log. So I'm going to say log of W is going to be equal to log of this statement right here. And I'm doing the exact same algebra that we did on the worksheet a few moments ago. We're going to say log of W is going to be equal to, now remember that rule that we could just do log and log. So we're going to have log of this animal, okay, so plus the log of this animal. All right, so remember that rule in algebra. All right, if you have a log of the product of two expressions or two factors, you just break it up into a plus. And then remember the other thing that you can do is you could just move this as a coefficient. All right, so we're going to finally say, or not finally, but we're going to say log is going to be equal to, we're going to say 0.258 dot times the log of A, right? And then finally, what we can do is we can get the exponential. We can take the exp of both sides. So W is going to be equal to exp of this stuff right here. All right, so this should be the equation of our linear data. All right, so now if you wanted to, what you could really do is just go back here. And we know that alpha is 0.825 and beta is 0.258. And we could just go right here and we just plug it in right here, all right, if we really wanted to. But I just went through and did the algebra just because I'm a math dork and it's what I like to do. All right, so this is our linear model. Okay, so all of this stuff is really inconsequential. All right, so we don't really need that. I was just illustrating the algebra to go through it, okay? But that's fine. Next thing we have to do, I forgot, is we're asked to find the function to linearize, create a scatter plot of the original and the power model next to one another. All right, so what we can do is we can say that we're going to have a subplot 1, 2, 1. Right, so remember that function subplot 1, 2, 1. That means we have one row, two columns, and we're looking at the first of those two graphs. And let's plot W comma A. All right, now lowercase w and lowercase a. And that's going to be, let's just put that as these guys right here. Now this is going to be, so we're going to say that this is going to be our W, which is weight. All right, and weight was in kilograms, I believe. And the Y label is going to be surface area. And I believe that was in square meters. Let me just verify that just to make sure. It might be centimeters. I don't want to lie. All right. So it wasn't kilograms and meters squared. Okay. So we have that. And then we're going to have our title. And this is going to be our original data. And that's going to be weight versus surface area of humans. Okay, so we have that. That's great. Now, the other thing that we have to do is we have to plot the nonlinear data, all right, or I'm sorry, the linearized data. This is the nonlinear data. I apologize. So what we have now is we have W versus A, all right? So now that we have this model, let's define capital A, all right? And that's just going to be the original data. So I could have just used lowercase a, but this is the data that we had originally, so I'm just going to cut and paste it. That's our linear model. And now what I'm going to do is I'm going to create another subplot. Now I'm just going to copy and paste this. All right, and I'm going to cheat. And this is going to be our 2. I'm going to plot now capital W and capital A, even though lowercase a and uppercase A are the same. We still have the same units. But now this is the linearized data. All right, now let's run this and just see what type of relationship we get. And hopefully I did all the code correctly. All right, so something went wrong here. Invalid indexing. So, symbolic there. Oh, let's try W and A. Maybe that'll help. Not sure. Same thing. All right. So it's telling me that there is an error. Well, it might be here. So we really don't need any of this stuff. So let's just cut this out. And right here, we have a W. We don't really need that right now. So I'm going to comment that out. Let's run it again. Okay. So it was somewhere in there. That's fine. Maybe I defined W twice. No big deal. All right. Now check this out. This is really cool. So this is the nonlinear data. All right. So we don't have a model. We do have a model for this, and I can put the model in the same graph if I chose to. But this is it sort of looks like it's linear. But then we hit it with the linear relationship, and we get almost a perfectly straight line. All right. So that's really cool that that we could just linearize the data, and it looks like a perfect line at this point. And now what we could do is, if I really wanted to, I could plot that model on the same graph. I'm not going to, right? It looks like my Matlab might have frozen up on me, so I'm getting spin. So let me give it a moment to hopefully unfreeze, and hopefully it doesn't crash on me. In the meantime, what else do we have to do? We have to find the correlation coefficient and then print the correlation coefficient and the equation of the linear model to the screen. All right, so that's pretty easy. So, all right, so correlation coefficient. So remember core, or we can say R is equal to core coef. And that's going to be, remember, our linearized data is A and W, capital. So I'm going to say A, comma W. And we're going to F print F. And we're going to say the correlation coefficient is, let's say, %F. And we're going to backslash n to go to the next line. And we're going to say that it's going to be R1, comma 2. So remember that trick from before. We're just looking at just that first row, second column. All right, we don't need everything in there. All right. And then, of course, we need it says the least squares line. So we're going to say P is equal to polyfit. We're going to say polyfit A or W, comma A. And I probably should flip this around. Yeah, it was WA, excuse me. So this should be, because weight is going to be explanatory and A is going to be the variable affected. So this is WA, and we're going to get a first degree polynomial. And so let's make a LS line variable up here. And we're going to say LS line is going to be equal to P1 times X plus P2. All right, and we should probably make X a symbolic variable as well. I try to refrain from using X as much as possible. All right, so let's F print F the least squares line. So fprintf, we're going to say the equation of the line is, let's say, %s, right? So we need a string, and that's going to be comma ls line. So let's see if that prints out and works. So we should get the correlation coefficient, which should be pretty good. When I say good, I mean close to +1. And then that'd be f right here. And then this should just give us the equation. So let's run it, see what we get out of it. Okay, so here's our subplot, and correlation coefficient is 0.99956. So it's like somebody almost made that up. Notice it's not perfectly 1 either. Okay, so and we should expect that. It shouldn't be 1, because if it was 1, that means that somebody fabricated it. All right, and that also means that the original data was a perfect fit. Right? One thing we might want to do is we might want to plot the original curves on each of these lines if we wanted to, just to see like how close they were. I'll just do this for this guy right here. So, so right here, I'm going to put a hold on. And right here, what I can do is, now we know that the range of values is 70 to 90. So I'm going to define x1 to be equal to 70 colon 0.1 or 0.1, excuse me, colon 90. And let's say y1, and this is going to be using the model, is going to be equal to, remember our original model, 0.825 dot times x1 dot raised to the 0.258 power. Right. And I'm just going to plot x1 versus y1 and hold off. All right, so let's see what that looks like on the original graph. All right, and it looks like a linear relationship, and that's just because we're so close in on the y-axis. It's like in your calculator, you zoom in an exponential, and it would actually look linear, even though it's not linear. But this is pretty close to each of those data points. All right, so it's not really all that far off, especially considering how wide the x values are in compared to the y values. All right. Now over here, if we were to create a least squares equation, and let's plot that on here, that'll be the last thing we do. Pretty clearly, this is going to be almost a perfect association. All right, just by linearizing the data. So right here, what we can do is I'm going to move this subplot down, because that way we have the equation of the least squares line. And let's just do this. Let's call this x2. And x2 is going to be the same thing, 70, 0.01 to 90. And we know, let's just call y2 equal to the same thing that the least squares line is, except I'm just going to say y2 is equal to x2. And I probably should say dot plus, even though it probably doesn't matter much because it's linear. And right here, I'm going to do the hold on. In fact, I'm just going to copy this data right here, do the same thing. And I'm going to call this x2, y2. All right, and that should give us, I'm not sure how that started running, but it did run. I didn't want it to run. Maybe I accidentally hit the run button or something. All right. So our data kind of got chopped off here. Not sure what happened. Maybe it was in the process of running or something like that. So let's try it one more time. Oh, that's right, because it's a different different domain. So let's do this. Let's say x2 is going to be our max of whatever. Let's do this, whatever the plot was. Let me cut this out. I'm going to comment this. And again, we're just trying to get to see what's going on here. So let's run this. And this way I can just see so it should be from like 1.03 to 1.06. All right, so let's do this. Let's do 1.03, and I'm going to do 001 and 1.06. All right. I forgot the scale was different than previous, which is why we're getting something weird. And then let me turn these comments off. All right, let's run it one last time, and hopefully this does what we need it to do. Yeah, we can see that this model is pretty close to this one up here. And notice that the units are so much closer together. That's why we don't have that much disparity in between. If the units were much closer together, then we can clearly see that these original data points are going to be close to the line. Um, so this is being able to just use some algebra to be able to compare a nonlinear association, hit it with that transform. So in this case, we just hit it with a logarithmic transform because it was a power transform or a power original. And then I went a step further and actually plotted the two models on both the equations. And we can see that the linearization kind of zooms it in a little bit, gets a little bit tighter for us. That way our domain isn't as large. Clearly over here, our domain's like 20, and then right here it's what, like 0.03 or something like that. So we get a lot easier, or we have a lot more limited domain to work with. Okay, so we've seen how to go through and work with our linear associations. We found correlation coefficients. We found least squares lines. We've graphed everything. We've hit everything with these sorts of transforms if necessary. So in our final video, or two videos that we're going to look at how do we analyze the error, and then we're also going to culminate everything into some sort of example where we're going to pull data from an Excel file, use Matlab to manipulate it, and then export it back into our Excel file.